Hello and welcome to the second part of Supercomputing with Versatile Data Backends. And in this lecture we're going to cover how we actually apply the ACIS to create a data-driven workflow. So specifically we're going to cover the ACIS engine, which is a submodule of the core ACIS library, which has been set up for processing workflows that use extreme data. We are going to focus on workflow orchestration, also parallelization within the workflow, and also how we manage access to different data backends by using the ACIS data system adapters. So, how do we apply the ACIS then to create a data-driven workflow? To start off, we need to use an orchestrator, a piece of software. We're using Airflow, which allows us to build, schedule, and monitor data pipelines. You can think of Airflow as the orchestration layer in our computational stack, in which we plug in the ACIS, which will then provide us with the task logic and data adapters that we need. Airflow has 4 components to it. You have a web UI, which allows you to inspect logs, view task lineage, view task states, and also timings with Gantt views. There is a scheduler, which decides when each task will run and moves tasks through states. There is an executor, which is the component that actually runs the task instances, and also a metadata database, which serves as a system of record for your Airflow deployment. So then, how do we define Airflow workflows as code? We use directed acyclic graphs, or DAGs, and these are graphs which are made up of nodes, which represent tasks, which are connected by directed edges, which represent the task execution dependencies. And in this example here, A has to fire before B, A must happen before B occurs. They're acyclic, so you can't loop back to where you started. There is a topological order. As a graph, there is a structure for expressing dependencies and concurrency. And DAGs are also written in Python. So you have all the features of Python, such as version control and reviewing, etc. Airflow is also extendable. You can install software packages known as providers, which provide Airflow with extra functionality. You have operators. These do the work. So you have ones for Kubernetes, HTTP, SQL. There are hooks, which provide connections and clients to external systems. There are sensors, which wait for external conditions to happen and then fire. And you have extras, which are optional dependencies, and integrations, which you can enable as and when needed. So we've come to the first demo then of Airflow, and we'll cover the installation of Airflow, navigating the UI, and also some DAG example code. Okay, I'm going to take you through the installation of Airflow. Then we'll take a look at the Airflow UI, and then we will have a look at some DAG code. So I have a script set up here to install Airflow. If we just take a look at it, initially it will create an Python virtual environment for Airflow. We then go on to install Airflow using pip. We then initiate the metadatabase. So then we can create an admin user for our Airflow instance, and then we start Airflow, first by starting the web server, and then we start the scheduler. Okay, so let's go ahead and install. This may take a minute. Okay, it looks like things are going okay. I should mention that this script is bundled with these videos as well. Okay, so now we're initiating the metadatabase. Creating the admin user. And now we start Airflow. Great, there we go. Okay, great. So that's Airflow now installed, and next we will take a look at the UI. So now you've installed Airflow and you have now logged in. This is the home page of Airflow that you're greeted with, and we are currently on the DAGs tab. What is displayed here is just an overview of all the DAGs which are installed onto the Airflow installation. You have the DAG name here, you have the owner, you have the amount of successful and unsuccessful runs, you have a schedule, you have the last date and time of the run, you have a next run which would be scheduled, and you have the recent tasks which have run on the DAG, whether it's been successful or unsuccessful. And up the top we have the main menu. What I'm going to cover here really is the essentials for this demo. However, there are other videos that we've provided on Airflow which cover Airflow in more depth, but for this demo I'm going to cover just what we need to know for this demo. So I will then go into the DAG itself. Open it up here. Okay, so this is a specific overview of the DAG. And what we see here on the left is a timeline matrix with the tasks listed as rows and the time as columns, and whether or not the run has been successful in green or has been unsuccessful in red. Okay, and if we click on the graph tab in this table here, what we see now are the individual tasks which make up this DAG. And for this DAG, so it's named as CBS3 demo. This is the demo which is going to be run later on in the second demo. But this is our DAG, which is made up of 3 tasks which come together to form our ETL process. So if I click on the DAG task itself, we expand the menu, and what's interesting to us here are the logs. So the logs provide the output for each task, and what you can see is an output from the task, which is providing us the first 10 lines of the raw data, which will be transferred onto the HPC system for processing. And we have some bash output as well, because essentially we are running a bash script here. So if we go back to the graph, then we can then look at the transform task, which again, if we go to the logs, just for information, these logs are from a previous successful run. So this is why we have command exited with return code 0, because it was successful the last time it was run during testing. But this just gives you an overview of the bash script which was run. And in this instance, for the transform task, we are connecting to a Dask cluster, and we can access the dashboard of the Dask cluster, and as our process was completed successfully, we have a process complete, and then the process exits with a code 0. And then our load task, we have the logs, which just show the output of the load task, and in this instance we are literally just piping out the first 10 pieces of data which have been cleaned, and then we exit the process. Okay, so now we can move on to the code itself. Here I've put in some extensive comments just to see what you can actually put into your DAG. So some DAG coding guidelines. Your DAG should be idempotent, meaning the DAG can run once or many times and the state or result will be the same as after the first time. Your DAG must be atomic. You want to avoid top level codes and keep complexity to a minimum to help performance and help scheduling. So if we scroll down, then we can see examples of operators which are available for Airflow. These are the Airflow official providers which can be installed onto your Airflow instance. So if we look, we have ones for databases, we have ones for HTTP, Slack, Teams, AWS, containers. We've also included Python as well. So we have operators for specific languages. Hook examples, you have them for databases as well, for cloud storage, for networking. Also sensors as well, which can be configured for files, things like time delta differences. These are all incorporated or can be incorporated into your Airflow instance. So we then move on to the actual DAG code now, and we import the bash operator, because what we are essentially doing in our task is we're executing a bash command. As we are deploying our ETL transform process, so the main bulk of the processing is being done on HPC. We need to provide HPC details so we can deploy that remotely. So we have the remote host, we have our version of Python that we want to use, and also a reference to our scripts which we want to execute. So we have the ETL extract, ETL transform, and ETL load. Okay, so then we have some standard DAG notation here, default arguments, which incorporate things like the owner, whether it depends on a past run or not, start dates, and how many retries we want to put onto the DAG. We then define DAG. Here we'll give it an ID, which is a unique reference to this DAG. We enable the default arguments. We give a description, and we are not using a schedule, so we do not create an automatic schedule for this DAG. So then we move on to the operator definitions. And these are all instances of the bash operator, and we essentially call a bash command in our bash operator. So for example, here, as we are accessing the HPC system remotely, we want to execute an SSH command directed at our remote host using our version of Python, and we carry out the ETL extract process by calling the ETL extract script. We go into the transform data task. Again, we're using the bash operator, an SSH command which calls the ETL transform script. And then we have load data, which uses the bash operator again, and we call the ETL load script via SSH this time. Okay, so these don't run all together at once. There is a task dependency topology here, and it will start with the extract data, wait for that to finish. It will move on to the transform data, and then it will move on to the load data. Okay, and that's the overview. So how can we introduce HPC into the workflow pipeline? We use Dask, which is a Python native parallel computing library. And what Dask gives us is auto-parallelization of codes. It provides two APIs, one high level, which provides the auto-parallelization data structures, such as the Dask data frame or the Dask array, and one low-level API, which gives you more fine-grained control over task creation or task dependencies. Dask is easy to deploy, so you can essentially write your code on a single core laptop, and then you can take advantage of Dask's adaptive scaling and run the same code on a multi-node cluster with no major rewrites required. Dask is compatible with HPC deployment patterns, so it's compatible with Slurm. Like I mentioned, it provides adaptive scaling. Dask is also compatible with containers, and Dask also provides a diagnostics dashboard to let you monitor your computation as it runs. However, when is Dask not appropriate? So don't use Dask when your application runs on a single node or your data fits into memory. You should then consider using an alternative Python library such as Pandas. If your runtime per task is less than 200 microseconds, Dask will add around 10 microseconds per task so there will be overheads which will occur and cause slowdown of your application. Also, if your application relies on heavy communication between Dask workers, then it would be advisable to use something like MPI to coordinate that. But Dask is appropriate when your data doesn't fit into memory on a single machine. If you have existing codes in NumPy or Pandas that you would like to scale up, you can implement Dask. If you would like parallel computation enabled across multiple cores or nodes, Dask will enable this. Like I mentioned, if your data doesn't fit into memory, you're using large data sets which incorporate or use many files, Dask is appropriate in this circumstance. Or you would like to take advantage of the lazy evaluation or the built-in fault tolerance or cluster scheduling that Dask provides. So, Dask is made up of 3 core components. So they have the collections, which are the auto-parallelization data structures, such as the Dask array or the Dask data frame. You have the lazy task graphs, which serve as a representation of your computation. And you also have the schedulers, which coordinate the computation. So then how does Dask integrate with the Akas engine? The Akas engine serves as a framework for parallel task deployment, and it leverages Dask capabilities for data processing, essentially providing functionality for task management, for distributing tasks, and also functionality for execution modes, whether it should be executed locally or remotely via a Dask cluster. The Akas engine then is made up of 3 core components. First, we have the Akas engine interface, and this facilitates Dask cluster connections. We can define execution modes, whether the task should be executed locally or remotely via a Dask cluster. And also it provides utility methods to submit distributed tasks and also exposes REST APIs. There is the Akas data structure, which is the Akas data frame, and this is primarily used for data handling. And we have data system adapters, which serve as operation packs, and they encapsulate basic operations for vector databases, relational databases, or object stores. And within the Akas collection, we have airflow providers for iRods and Milvis. So we've come to the second demo, and what will be covered here is an example DAG of an ETL process, and we can use the diagnostics dashboard to look at the computation as it runs. So here we have on the right Airflow, and we have the details tab open, which is for our demo DAG, which in this case is an ETL process. And on the right hand side we have the Dask UI open at the Workers tab. And what is shown here is each worker that we have deployed on the HPC system and their status. Each worker has been assigned to one CPU and is managed by the task scheduler. And currently all our workers are in an idle state. So then if we move over to the status tab, this will give us a live update of the computation as it happens. We'll see each worker being executed. Okay, now we'll trigger the DAG. So first we have the extract process, which is essentially copying data from an external source over to the HPC system. Okay, and here is an example of that raw data. Now we kick off the transformation process, and we should see Dask kick in as well. There we go. So now we're preparing the computation, and if we move over to the graph tab, what you'll see is the task graph for the actual transformation process, which in this instance is a basic MapReduce function. So we move back to the status tab, and we should see each worker start to execute. Okay. And here we see the progress of the computation as well. Okay, and it's finished, and now we move over to the load process, and we just load a sample of the transformed data.
Ladies and gentlemen, this is Stefan Hachinger from Leibniz Supercomputing Center, the Science and Co-Design Coordinator of EXA4MIND. For the end of this webinar, I would like to quickly point you on some further resources you can find to apply the techniques that you just seen and to understand how EXA4MIND supports you in all that. The aim of this webinar, which came in two parts, was to show you how supercomputing works with optimum data backends. We presented you how modern object store and database options can improve your data handling, how EXA4MIND helps you to install these systems, and how you work on these systems with the advanced query and indexing system ARCIS that EXA4MIND provides. ARCIS enables you to execute workflows with Airflow or with Dask. The techniques that we have shown you can be used on systems from the laptop to the supercomputing scale, depending on what you have available. To understand the setup of the ARCIS of the backends and the combined use of it better, we provide you some further resources on the web. On this slide you see the links to the documentation and to our open source repositories. We thank you very much for your interest and are happy to welcome you again for other webinars in the EXAKI series.